We first started talking about a secant line. A secant line touches our function in two different places. And we saw that as we moved those two x values closer and closer together, that secant line changed slope. We found the slope of the secant line using pretty much the old slope formula that you used from Algebra 1. And then we started modifying that a little bit into the difference quotient, which looked like this. And we got things in terms of h, and then we started saying, well, let's start talking about this limit idea, that as those 2 points get closer and closer together, when we reach the limit, then what have we got? And it turned out that we had the slope of the tangent line. So here's the official definition of a tangent line with a certain slope. Notice we're talking about the change in y over the change in x here, which is really just a modification of the old slope formula. In this form, we're talking about a point C, which is some definite x. We're talking about some change in x, which we used to call h, and we're talking about C over here also. That would be our y1. This would be our y2. And this delta x down here, the change in x, is the distance from the first point to the second point on the x-axis. And as we go through this, I want you to notice how similar what we're talking about in section 2.1 is to what we did with the difference quotient before. And as these notes point out, we might end up with vertical tangent lines in some instances when the limit doesn't exist because it's going to positive or negative infinity. So we'll talk about those later. For right now, let's see if we can find the slope of these different functions at specific x values. So for the first one, our function is 3x minus 2. So every place I see an x, I'm going to put x plus h. So I've got 3 times x plus h minus 2. There's our y2 minus our y1 all that's over what? H. Okay, I'll multiply, so I've got 3x plus 3h minus 2 minus 3x plus 2. All that's over h. I'll see if I can cancel out some things here. So my 3x's cancel. Negative 2, positive 2, which leaves me with 3h over h. And what we're interested in now is, well, what does that leave us as h goes to 0? First, let me cancel out my h's. What does that leave us as x goes to 0? Well, the limit of f of x as h approaches 0 is just 3, which is not a great shock because we're talking about a straight line, and we can see the slope is 3 back here, even just looking at this equation right here. Slope is 3. So whether we're talking about x equal to 4 or x equal to 10 or x equal to negative 15, that slope is going to be a constant 3 because it's a straight line. Now notice that might not be the case over here because we've got in part B f of x is x squared. not a straight line. That means that the points along that curve, the slope is going to be changing constantly. So let's go through this. And I've got my function is x squared, so I put x plus h squared, there's my y2, minus, not that, minus x squared over h. Okay, that gives me x squared plus 2hx plus h squared, then minus my y1. All of that's over h. What cancels? My x squares, and that's about it on canceling. So what I've got then is 2hx plus h squared over h. Let's do a little bit of factoring. I can pull an h out on top, and that's going to give me 2x plus h over h. I can cancel my h's, which now leaves me 2x plus h. Now we're interested in the limit of that as h is going to 0. Well, when h goes to 0, the limit is just 2. So that means what I have found, 2x. What I have found is that anywhere along that curve, if I know the x value, I can compute the slope. So at x equals 3, my slope is 2 times 3, which is 6 at this point right here. If we're talking about the point x equals -4, my slope would be 2 times -4, -8. See, the slope is changing as we move around that parabola. It's not a constant value like it was with a straight line. Now in calculus, there's two big operations going on, major categories. One of them is differentiation. That's what we're looking at here. And the other is going to be called integration. They do two different things. So we're looking at differentiation right now. And the process we just went through is called finding the derivative of some function at some value x. Now I'm trying to put definition kind of things in red, so I've got a red box around derivative. But notice in the green box, it's got f with an apostrophe x. Well, it's not an apostrophe. That notation is called f prime. That's what that thing in the green box right here is. F prime, which stands for the derivative of f at x. Now they're using the delta x form here. It's just like the h form. Instead of h, they're saying delta x, the change in x. And instead of h on the bottom, delta x, and so on. So let's use that because they're doing it. Now then, something really important to notice is right here. F prime is still a function. It's not just a value, it's a function of x. Keep that in mind. So I've got my green boxes down here at the bottom with a star, which sort of indicates these are pretty important. By finding the derivative of a function, I can get the slope at any place on that curve. No matter what the x value, I can plug that x value into my derivative function, f prime, and get the slope. Also, by doing that, I can find things, as it's saying down here at the bottom, the instantaneous rate of change. Well, the slope of a line is measuring the rate of change if you get right down to it. But now then we can find that instantaneous rate of change anywhere along the curve. you'll see as we go along what I'm talking about there. So in terms of the derivative, if it actually exists at a certain x value, then we use the term differentiable at that value. A function can be differentiable over an interval as long as the derivative, the thing we just looked at, exists at all the x values. In the next green box here, please notice that f of x refers to the original function. F prime of x is talking about the derivative, which again is a function. Okay, check this green box out. Here's several different ways of writing the derivative. F prime of x, dy dx, y prime, and so on. You'll see any or all of those in our course as we go through it. Right now we're using f prime, but we'll use the others. So just be ready. And then down here in this green box, all of those things mean the same. Dy dx is the same as the limit as delta x approaches 0 of the change in y over the change in x, which is the same as the limit as delta x approaches 0 of this thing that looks like the difference quotient, which is also the same as f prime of x. Bunch of different things that mean the same thing. So on different problems we might have to mix and match a little bit. Let's use their definition of a derivative to figure out what the derivative of this function is. X cubed plus x. Alright, we're going to use the delta x form. So my function is x cubed plus x. Every place I see an x, I'm putting x plus delta x. So I've got x plus delta x, meaning the change in x, cubed, plus x plus delta x. So this is really my y2 right here. And I subtract from that my y1, which is just the function the way it was originally written. All of that's over delta x, and we're wanting the limit of this as delta x approaches 0. Now I'm looking at this first thing over here, this. We can FOIL that, we can square it and then we can FOIL it again. When you do, it's going to turn out to be x cubed plus 3 delta x squared plus 3 delta x squared x minus, plus delta x cubed. Alright, that's our y2. Now I'm going to subtract my y1 stuff from it. So I've got x cubed. It's not a plus though, is it? It's a minus x right here. Minus x. All of that's over delta x. We're still looking for that limit. Okay, let's see what cancels. So my x cubes do, is that it? Yeah, I think it is. So let's use the definition of a derivative to find this limit definition. Okay, so my function is x cubed plus x. That means every place I see an x, I'm going to put x delta x, x plus delta x. So I've got x plus, I'm going to just use the H version. Okay, let's use the definition of a derivative to find this derivative. Alright, I'm going to use H instead of delta x because it's easier to write. So my function is x cubed plus x. So every place I see an x, I'm going to put x plus h. So I've got x plus h cubed plus x plus h. That's my y2 minus x cubed plus x. There's my y1. All of that's over h, and we're wanting the limit of this thing as h approaches 0. Okay, let's do some multiplying here. So I'm going to cube x plus h. When I do, I'm going to get x cubed plus 3 h x squared plus 3 h squared x plus h cubed. That's what I get when I do this part right here. Now, you can FOIL all that out. If you want to know how I got that without foiling it, just ask me. It's pretty cool the way that works. But that's what you're going to get. And then we're going to subtract this part out here, our y1. So that's going to be minus x cubed minus x. And all of that is over h. And we're looking at the limit here as h goes to 0. Let's see what cancels. X cubed, x cubed. Is that it? Let's use the definition of derivative to find the derivative of this function right here. Now I'm looking at my function. It's x cubed plus x. That means every place I see an x, I'm going to put x plus h. I'm not going to write the delta x version just because it's harder to write, especially online. So I'm going to put x plus h cubed plus x plus h. So there's my y2 version of it, minus the y1 version of it, which is just x cubed plus x. Okay, I'm going to cube this right here. Now you can do it by foiling, and that'll work. Or you can use a technique that, if you're interested, we're looking for the limit here. God. So let's use the derivative definition to find the derivative of this function. My function is x cubed plus x. So every place I see an x, I'm going to put x plus h. So I've got x plus h cubed plus x plus h. That's my y2. I'm going to subtract my y1. All of that's over h, and we're wanting the limit as h approaches 0. Now you can FOIL to get this right here, or there's another technique you can use. It's a lot faster. If you want to know how to do it, get with me. But what I'm doing here, I'm going to end up with x cubed plus 3hx squared plus 3h squared x plus h cubed. That's what I get from cubing that first term in there. Then plus x plus h. Now that's all my y2. And I'm going to subtract this y1 out here from it. So I've got minus x cubed minus x. All of that's over h. And we want the limit as h is going to 0. Okay, let's see what cancels. X cubed minus x cubed. I've got x minus x. And that's going to leave me, I believe, with 3h x squared plus 3h squared x plus h cubed plus h. All of that over h. Okay, stay with me. I can pull an h out of all those terms on top. So I can say h, and that leaves me 3x squared plus 3hx plus h cubed. Nope, sorry. Let me think here. 3x squared plus 3hx plus h squared plus 1. Alright, all of that is over h. Well, I can factor these h's out, cancel them, and that's going to leave me 3x squared plus 3hx plus h squared plus 1. And no more denominator. So stop right there. Let's make sure I did it right. And again, we're interested in the limit as h approaches 0. Well, when h approaches 0, what's going to happen? A 0 in here is going to cancel that out. A 0 here is going to make that 0. So that's going to leave me with this limit, 3x squared plus 1. So there's my derivative. It's based on the limit. There's my derivative. Okay, there's my f prime. Again, this is a function. Notice it's a function of x. Now then, if we wanted to find that's the slope of my function, I can plug in any value I want to for x and I'll get the slope at that point. For instance, if I plugged in 2 for x, I could say f prime of 2 equals 3 times 2 squared plus 1, which would equal 12 plus 1 equals 13. So when x is 2, the slope of the tangent line at that point is 13. Pretty cool. Here's an alternate form of the derivative definition that you'll see sometimes. It's saying the same thing if you stop and think about it. If you compare this to the form that we used before. Now it does require, check the green box out, it does require that the one-sided limits do exist and that they're equal. That's not too different from what we've talked about before. The limit coming from the left and the limit coming from the right have to be the same. Right here is telling us that if a function is differentiable at a point, it's continuous there. On the other hand, if it's not continuous at a point, it's not differentiable. Now get that in your head. If it's differentiable, it's continuous. If it's not continuous, it's not differentiable. Let me write it out a different way. If it is differentiable, it is continuous. If it's not continuous, it's not differentiable. Please notice what this thing is not saying. It's not saying if it's not differentiable, it's not continuous. It's not saying if it is continuous, then it's differentiable. Make sure you understand the difference in what it is saying and what it isn't. Here's a for instance. If I had the absolute value function, as I'm approaching 0 from the right, the slope of that function is positive 1. As I'm coming at 0 from the left, the slope is negative 1. Now that function is continuous, but it's not differentiable because those limits are not the same as I'm approaching 0. So I just want to illustrate, this is not being said down here. So don't make that mistake. And in the notes themselves here, notice it says continuity does not imply differentiability. Just because it's continuous doesn't mean it's differentiable. And there's that absolute value function again. Highlighted in green, we now have the capability of finding the equation of the tangent line at any point. How are we going to do that? Well, first, let's find the derivative. So for a, I'm going to say now my function is 2x squared minus x. Every place I see an x, I'm going to put x plus h. So I've got 2 times x plus h squared minus x plus h. There's my y2. My y1 is 2x squared minus x. All of that's over h. We're wanting the limit as h is moving towards 0. Okay, I just start doing the math. I square the x plus h, and I'm going to get 2 times x squared plus 2hx plus h squared. That's what I get from squaring this right here. And then I've got minus x minus h. There's my y2 spread out a little bit more. I'm going to subtract my y1 over here. So I've got minus 2x squared plus x. All of that's over h. We're wanting that limit. I'll multiply by my 2 up here on top, and I'm getting 2x squared plus 4hx plus 2h squared minus x minus h minus 2x squared plus x. All of that's over h, and we're wanting that limit still. Let's see if anything cancels. 2x squares do. I've got a negative h and a positive h. I think that's all it's going to cancel. So let's see what we got. When the smoke clears a little bit, I've got this. I can factor out an h on top. So I've got h times 4x plus 2h minus 1 over h. Still talking about the limit. I can cancel those. And that leaves me the limit as h approaches 0 of 4x plus 2h minus 1. Now as h is getting closer and closer to 0, what happens? When h becomes 0, that goes away and leaves us with the limit of 4x minus 1. That's my f prime. That's a straight line. Okay, so our original function is a quadratic. It's a parabola. The tangent to it, I've got a straight line going on. I can find, now then I can say, well, okay, what's the equation of the tangent line? And I've got to go back to some Algebra 1 techniques. Let me erase some of this stuff so we got a little more room. Okay, all I left here was what f prime is. Now that says I can calculate the slope at any value for x. Well, I know my x value is 2 over here, so f prime of 2 equals 4 times 2 minus 1 equals 7. So I know when x is 2, the slope at that one point is 7. Okay, how does that help me? Well, now I go back to that Algebra 1 stuff I was talking about, and I know that I can use this form, y minus the y that we're talking about, the point slope form. So I'm going to plug in 6 here, equals the slope times x minus the x value. This is from Algebra 1. I'm just plugging in the 6 from the point they gave me and the 2 from the point they gave me. So I've got y. I'm going to add 6 to both sides. So I've got 6 plus 7x minus 14. Okay, so I've got y equals 7x minus 8. And that would be the equation of the tangent line. So here's our original function, 2x squared minus x, and here is the line y equals 7x minus 8. Now where x is 2, we come up and we know that the y is 6, and right there at that point is where this blue tangent line is touching our curve. Anywhere else on that curve, the slope of the tangent line would be different. Let's try B here. Okay, so I've got my function is the square root of x plus 3 plus 2. So every place I see an x, I'm going to put an x plus h. So I've got the square root of x plus h plus 3 plus 2. There's my y2 minus the square root of x plus 3 plus 2. All that's over h. We're wanting the limit as h approaches 0. Okay, when I remove parentheses, I've got square root of x plus h plus 3 plus 2 minus the square root of x plus 3 minus 2. All that's over h. Let's see if anything cancels. So the 2's do, well, which leaves me with square root of x plus 3, x plus h plus 3 minus square root of x plus 3. All that's over h. Okay, so I'm going to multiply that by square root of x plus h plus 3, hang with me, plus x plus 3 on top and bottom. So I'm multiplying by 1. On top, still talking about the limit. On top I've got this thing squared, which brings it out from under the radical. So I've got x plus h plus 3. Since this is a difference of two squares, that means I've got this thing squared, which brings it out from under the radical, which gives me minus x plus 3 over h times x, this ungodly thing, on the bottom. Okay, not pretty, but we're getting there. So what's going to cancel? Well, I've got negative h here, h, so those will cancel. I've got 3 and negative 3. So on top, that leaves me h, and on the bottom, I've got that nasty looking thing. So let me do this. H times x plus h plus 3 plus square root of x plus 3. All that's on the bottom. Okay, I can cancel my h's, leaves 1 on top. What's it going to leave me on the bottom? X plus h plus 3 square root plus the square root of x plus 3. Now think with me, as h is approaching 0, we're talking about the limit here, as h approaches 0. As h approaches 0, that means this is going to drop out, which is going to leave me 1 over the square root of x plus 3 plus the square root of x plus 3. Said another way, let me come over here, it's going to be 1 over 2 times the square root of x plus 3. That's my f prime of x. Can't say that wasn't fun. Okay, so let's hold on to that for a second and erase some of the other stuff. Okay, so clean it up a little bit. We've got f prime of x equals 1 over 2 times the square root of x plus 3. So now I'm going to plug in my x value where they're asking for it. They're wanting it at 6 for an x. So f prime of 6 equals 1 over 2 times the square root of 6 plus 3 equals 1 over 2 times the square root of 9 equals 1 over 2 times 3, so 1/6. Now what is that? That's the slope of the tangent line on this function right here at the point 6, 5. Let me say it again. 1/6 is the slope of the tangent line at the point 6, 5 on our curve. So here's Desmos. Here's our point 6, 5 right there. Here comes the tangent line. Notice it's touching at that one point, 6, 5. And also notice the slope of this thing. You can see right here it's hitting at 0.4. And so the slope is 1/6. That means every 6 to the right it goes up 1. So 1, 2, 3, 4, 5, 6. It goes up 1. So f prime, again, is the slope of the tangent line. So on 4, they're giving us the function and they're giving us a slope, and what we have to do is find an x value on that function where the slope is what they gave us. In other words, we're finding the place where the tangent line is touching the curve. So my f of x is this. So every place I see an x, I'm going to put x plus h. So I've got 1 over x plus h plus 2. There's my y2 minus my y1, and all that's over h. And we want the limit as h goes to 0. Alright, I've got to get a common denominator here, and so if I just multiplied those two things together, I'd have a common denominator. So that would be x plus h plus 2 times x plus 2. We'll get the numerator here in a minute, and all of that is over h. So what would it take to multiply the x plus h plus 2 by to get our common denominator? Well, the answer is x plus 2. So I put that on top times 1. And then that's minus the other side. X plus h plus 2. All of that's over h. All right, let's keep going, and that's the limit again. So on top, I've got x plus 2 minus x minus h minus 2 over that same denominator over h. Okay, so I can cancel these and these, which leaves me negative h over this over h. So I keep change flip, this is really h over 1. I keep change flip, so I've got 1 over h here. These will cancel. So I've got negative 1. So I've got negative 1 over x plus h plus 2 times x plus 2. Now, we want the limit as h is moving towards 0. Well, when h is going towards 0, what happens? This right here turns to 0, which leaves me negative 1 over x plus 2 times x plus 2, which is x plus 2 squared. Okay, that is my f prime of x. Now remember, that's the slope of the function. If I want the slope at any place along that function, all I have to do is plug in an x value. Well, the x value is what I'm looking for. So now what do we do? Well, let me clear out some of the stuff above so we have room. Okay, that cleaned it up some. Now I know that the derivative is the slope of the tangent line at that point. Well, they gave us the slope. So let's set this derivative equal to the slope. So I've got, and that was a negative up there, I believe. So I've got negative 1 over x plus 2 squared, our derivative in other words, equals negative 1 over 9. So I've got negative 9 cross multiplying equals negative x plus 2 squared. Just divide both sides by negative 1, so I've got 9 equals x plus 2 squared. Okay, I can use the square root property to take the square root of both sides, and so I've got plus or minus the square root of 9 equals x plus 2, which means that x plus 2 equals plus or minus 3. Take 2 away from both sides and I get this. So that means my x values, there are 2 of them, would be negative 2 minus 3, so it would be negative 5, and negative 2 plus 3 at 1. So when x is negative 5 or x is 1, the slope at those 2 points would be negative 1/9. I'd have 2 tangents to that curve, and those tangent lines would be parallel because they'd have the same slope. Interesting. So I went ahead and figured out the equation for the tangent lines. The green is our original function. Out here at -5, we can see where that tangent line hits our curve in one point. And the slope of that tangent line is -1/9, by the way. And then over here at 1, we can see where the second tangent line hits the curve. So just thought I'd give you a look at what Desmos has to say about it if you put the equations in. So let's get a little room for part B, and I think we're done. Here our function is 3x squared plus x minus 5. So every place I see an x, I'm going to put an x plus h. So my y2 is going to be 3 times x plus h squared plus x plus h minus 5. There's my y2. Subtracting from that my y1, so I've got 3x squared plus x minus 5. All that's over h. And we're looking for the limit as h approaches 0. So I square this right here, and I'm going to get 3 times x squared plus 2hx plus h squared plus x plus h minus 5. That's our, let's see, let me put the parenthesis where it goes here. That's our y2, and I'm going to subtract our y1, so that gives me -3x squared -x plus 5. All that's over h. Okay, and we're still talking about the limit, and so I've got, removing the parenthesis, 3x squared plus 6hx plus 3h squared plus x plus h minus 5 minus 3x squared minus x plus 5. All that's over h. Let's start canceling a little bit. So 3x squared minus 3x squared plus x minus x minus 5 plus 5. Is that it? So that leaves me 6hx plus 3h squared plus h, all that's over h. I can pull an h out, so I've got h times 6x let me think about this. Yeah, I think we're good. Times 6x plus 3h plus 1. Is that right? Yep. Okay. All that's over h. I can cancel these h's. Let me clear out some more room. So we're coming up here on this other side. I've got 6x plus 3h plus 1. Okay, now that as h is going to 0, what does that give me? Well, this term right here would go away. So that's going to give me 6x plus 1, which is our f prime. That's our derivative of x. Again, that's a function. Okay, now then, notice they're giving us the desired slope is 0. So I'll take our derivative, which is the slope of the tangent line at that point, and I'll say 6x plus 1, our derivative, equals 0 that they gave us. So 6x equals negative 1, x equals negative 1/6. So when x is negative 1/6, we'll have a tangent line at that point with a slope of 0. Now if you go back and look at our original function, 3x squared plus x minus 5, what kind of thing is that? It's a parabola. And where would a parabola have a slope of 0? It would have to be at the vertex, right? So let's graph that in Desmos and see if that's true. Here's the graph of that function, and here's the tangent line. And this point right here, right in there, is, well, I can get it better, closer to 1, negative 1/6, is right in here, and the blue tangent line is touching at that one point. Seems like it worked. Here's a more readable version of 3b. Got kind of squished down when we were doing it before, so I hope this one's easier to read. If you got questions, please get in touch with me. This is what it's like finding the derivative, at least right now. We'll learn a bunch of other techniques as we go.